Alright, that was embarrassing. Instead of streaming on YouTube, I streamed on Twitch. And, I don't stream on Twitch for education. Anyways, today's the second day of the midterm. I'm going to actually pin my own comment. I'm going to say, alright, these is the problem. Okay, so we're going to, unless if you guys know that, the, or unless if you guys know what problems, I'm probably just gonna continue. But let's go to the, I'm gonna go back to the book, which is the Precalculus book, graphical, numerical, algebraic, and see if I can get some stuff. 1, 2, 2, 2, 2, 3, 3, and 4. All right. All right. I'm gonna wait for people to trickle in, and then I will start. I will start. No data. All right. All right. There's one person watching right now. Okay. Um, so I'm gonna start. It's been 5 minutes, I think, since I've waited for 5 minutes. Oh, synthetic division with non-real numbers. It takes forever. Is there a trick for it? Let's see. So, I don't know off the top of my head, but I can try to figure one out right now. So let's say we have a x squared plus, no, let's say x squared plus uh x squared plus 1 equals 0. So x squared would be -1. So x would be plus or minus I. So if you take x squared plus 1, that's 1, 0, 1. And then this would be, well, x minus I, right? So then it would be I. So if I'm dividing x squared plus 1 by x minus I should be getting x plus I back. So let's see what I get. If I put 1 here and multiply by I, 0 plus I is I, multiply by I squared, -1, 0. Works the exact same way. Exact same way. That's the synthetic division for the imaginary numbers right there. And for non-real numbers, it's I think it'll work the exact same way too, but let me see. So let's say we have a little something with solutions 2 plus 5i, and then 4i, or no, 2 minus 5i, and then x minus 4. So x minus 2 plus 5i, x minus 2 minus 5i, and then x minus 4. So this is a trinomial. No, it's not a trinomial. I'm sorry. It's a cubic equation because it has three, or the highest term is x cubed. I'm going to multiply this out. I'm going to say this is x squared minus 2 plus 5i, 2 minus 5i. I can add them together to get 4x. 2 plus 2 is 4, and then 2 plus 5i times 2 minus 5i is 4 minus 25, which is, I should know this. 4 minus 25i squared is 29. Alright, so it's plus 29. So x squared minus 4x plus 29 times x minus 4 is x cubed minus 8x squared plus 45x minus 106. No, minus 116. Alright, so if I take this bigger polynomial, 1 minus 8, 45 minus 116, and divide this by, I'm going to say x minus 2 plus 5i, so it's 2 plus 5i. I can do 1, 2 plus 5i. And minus 8 plus 2 is minus 6 plus 5i. So, someone messaged me something. So 6 plus 5, minus 6 plus 5i, multiplied by 2 plus 5i is, well, minus 6 plus 5i times 2 plus 5i is minus 20i, minus 12, and then minus 25. So minus 37. Minus 20i, minus 37, which will get you minus 20i plus 8. Multiply by 2 plus 5i. Minus, I think it's going out of the screen, so let me make it smaller. Minus 20i plus 8 times 2 plus 5i is negative 40i plus 40i plus 16, and then plus 100. So it's 116, which will give you 0. So synthetic division with non-real numbers work exactly the same as synthetic division with real numbers. No change at all. There you go. Of course, you don't really want to find non-real roots. That is kind of stupid, to be honest. Uh, but you will be able to do synthetic division with these numbers if you really want to. Um, all right. What are the different types of function notations, and what do they mean? What do you mean by function notations? Like f prime or like f inverse? Like you mean f minus one? Oh, fg of x and stuff. Okay. Um. All right. Let's say f of x is equal to e to the cosine x and g of x. I'm not going to draw these. You're not expected to know how to draw these. Is negative 2 over square root of x plus 1. So what would usually I no sane person would write something else other than this, but sometimes the math textbook likes to do f plus g like this of x. This just means the addition of two functions. You add this function with this function. So that's e to the cosine x plus minus 2 over square root of x plus 1. That's f plus g. Now f minus g is f minus g. I don't think I need you to explain. Don't think I need to explain that to you. F times g, or f of x g of x, which is how you usually see it, but again, not everyone writes it like this. F g of x is the multiplication. Basically, look at this. If it's if it's being multiplied, then it's a multiplication. Similarly, f over g of x division. This is equal to e cosine x um, negative times negative, but I'm going to put the negative in front just so that it's a little bit less crowded, times 2 over square root of x plus 1. And then this is equal to negative e cosine x over 2 to the square root of x plus 1, which is also negative e to the cosine x times the square root of x plus 1 for 2. Now the tricky stuff. So f of g of x. F of g of x. Um, so f of g of x is something called a composition function. And it's easier when you do something like, I'd say, if you have something like x plus 1 squared, then you could say that f of x, the outside function is the squared. The outside function is like the squared, and then the inside function g of x is the x plus 1. So you would kind of superimpose the brackets onto the x plus 1 to then make it squared. So then this could be written as f of g of x, because what are you squaring? What are you putting inside? This would be x squared if it were just to be x right here, right? F of x is x squared. So f of the entire function g of x is x plus 1 all squared. So f of g of x here is, well, f of x is e to the cosine of x. So f of the function g of x is cosine of -2 over square root of x plus 1. Which is way different than g of f of x, which is you take the g of x, you take the g of x, and then instead of putting x in there, you put f of x in there. So -2 over square root of f of x e to the cosine x plus 1. So those are that's the composition notation. What about f of x? F of x is you take f of x e to the cosine x, and then you put another iteration of f of x, or you substitute the x on top for f of x. So you would get e to the cosine x again. E to the cosine, e to the cosine. All right. Any more questions? What happens when it's a circle that isn't filled in? What do you mean? Like a semicircle? Or are you saying about the like f of g of x, like that? Like fog of x? Fog of x is f of g of x. The left function is outside and the right function's inside. Um, all right. The left function's outside, the right function's inside. It's bad. I hate the notation. It's so terrible. But it's that's how the notation works. F of x. Just treat the O as like an of. The open circle, treat it as an of. So this would be read f of x. So it's just f of x. This is f of g of x, f of g of x. All right. Okay. If there are no more questions, I'll just go back to the 12 basic graphs. Um, basic with quotation marks, with heavy quotation marks, because most of these aren't really basic. The 12 basic graphs is, I think the graphs that you see in 1.3, chapter 1.3, and they are very, you have to know them. They're, or you don't have to know all 12, but you have to know a lot of them. They are vital, very, very important. So, the first basic graph is this guy. Very nice. Y equals x. Y equals x is a constant function. It's also called the identity. It's the identity because the identity is every x you get, right? If I have an identity, that means I am myself. So for every x x is itself, or y is equal to x. For every x, y is equal to x. So if I have an identity, I'm equal to myself. So for every x, y is equal to x. That's why it's called the identity function. Probably useless information, not useful for the final at all, but that just thought I would throw that out. All right. The next basic function is one that you probably have learned in Math 1, and the function is y equals absolute value of x, which is the same thing as y equals x on one side, but flipped on the other side. Y equals x is flipped along the x-axis on the other side. And that's because y equals the absolute value of x actually is a piecewise function that just happens to have angular speed and velocity. Angular speed and velocity? I'm gonna start saying stuff and tell me if it seems familiar or not, because I don't know what this means. Um, Unfortunately, I'm gonna start saying stuff and tell me if it's familiar or not, or tell me if it's familiar. Okay, if it's not, then just stop me and give me the chapter number. So the angular speed is omega, and the angular speed is the number of revolutions per number of or radians that it or whatever encompasses in a second. So angular speed is radians per second. So angular speed is also the angular displacement theta over time, specifically the change in displacement over the change in time. Now, what is the change in displacement? The change in displacement is the arc. It's I'm sorry, it's not the arc length. Um, the change in displacement is, well, if you're moving along like a bicycle wheel, ooh, or no, this is the change in angular displacement. So it's a change in angle, basically, not the change in actual displacement. So like this, if you're having this, then theta is the change in the angle that you're swooping over the change in time. That's called angular velocity. It's different from regular velocity. Angular velocity is measuring how fast you're rotating. Regular velocity is measuring how fast you're traveling. So if we want to turn this into regular velocity, how are we going to find that out? How are we going to find regular velocity out? Well, this arc length is actually, and that's why we put it in radians, the entire circle circumference is 2 pi r. But the entire circle's angle is also 2 pi. So it turns out that the arc length, this is what I call the arc length, is equal to the angle times the radius. So whatever angle it is, times the radius. 2 pi, the entire circle circumference, 2 pi r. Half a circle, pi r. 60 degrees, that's pi over 3. 60 degrees is pi over 3. You have to remember how to convert from degrees to radians. I think that was something that I emphasized. So degrees times pi over 180 is equal to radians. And similarly, radians times 180 over pi degrees. 60 degrees, pi over 3 radians. So 60 degrees of arc length in a circle pi over 3 times the radius meters. So the change in if we have this, if we have s is equal to this over r is constant, so the change in s, I'm using s as arc length, so the change in s is equal to the change in theta over r. um so the change in theta is equal to the change in s over r. So what does that mean? That means that the angular acceleration is equal to rad per second, or is equal to the change in theta over the change in time, is also equal to the change in s over the change in the arc length over r times the change in time. Right there. So how is omega different from just velocity? Velocity does not take into account this r. Velocity is simply the change in displacement, the change in this distance right here, or displacement. I'm gonna just use distance, um, over the change in time. Right? So it doesn't include the r. So we get this relationship. The relationship is v is equal to this, but w is equal to this. So w is equal to v over r. So v is w. Uh, wait, no. Did I say that wrong? But w is equal to this, and v is equal to this. So w is equal to v over r. So v is equal to wr. Hope I didn't get that wrong. Yeah, I did not. Okay. V is equal to wr. So you can deduce the same thing for acceleration. The acceleration, which I will use alpha, is equal to the change in omega over the change in time, which is equal to the change in omega over, or the change in v over r times the change in time. V is equal to, or I'm sorry, acceleration is equal to the change in v over the change in time. So that's equal to alpha times r. I don't know any practice problems, so I'm gonna try to find some. Trig, trigonometry, 4, 4, 5. 4, 4, 4, 3. I don't know. I don't happen to know which place this is from. Tan theta, 4, 3. All right, let's go up to 4, 2. No. What about 4, 1? 4, 1. All right, I don't know where to find problems of this type of caliber. Oh, right here. All right, right here. I found one. A radial arm saw has a circular cutting blade with a diameter of 10 inches. So diameter is 10 inches. I'm not going to draw it. I'm just going to draw it on the thing. Diameter is 10 inches. That means the radius is something. Uh, Figure it out. It spins at 2000 RPM, revolutions per minute. Not This is RPM right here is revolutions per minute, not radians per minute. Radians, it will say rad. RPM is revolutions per minute. Now, how many radians are in a revolution? Well, I already said the entire circle is 2 pi radians, so 2,000 revolutions per minute is 4,000 radians or 4,000 pi radians per minute. Now I just realized that I did not need to do this at all, because it's saying that if there are 12 cutting teeth per inch on the cutting blade, 12 cutting teeth per inch on the cutting blade, how many teeth how many teeth are crossing? Oh, how many teeth cross this cutting surface each second? All right. So 12 cutting teeth per inch. So first of all, let's find the circumference. What's the circumference? The circumference is 2 pi r. 2 pi r inches. So there's 12 cutting teeth per inch. So how many teeth is there? Well, 2 pi r inches times 12 per inch. So that's 24 pi r teeth. 24 pi r of the teeth. So we have 24 pi r of the teeth for every revolution that we go through, and we have 2,000 revolutions per minute. That means that the number of teeth that is crossing every minute is 24 pi r teeth per revolution times 2,000 revolutions per minute. Now, what else do we have to do? We have to turn the minutes into seconds. So how many seconds are in a minute? 60 seconds are in a minute. And the point of doing dimensional analysis like this is to make it cancel out like that. To make the dimensions at the bottom and the top cancel out. So every 1 minute is 60 seconds, so you put the minute on top, you don't put it on the bottom, because if you put it on the bottom, you would not get the dimensions would not cancel out, and you would get really nasty units. That's why sometimes it's good to work with units. Sometimes it's not really good. But in this case, it's good. You can cross out the revolutions, cross out the minutes. 24 times 2,000 divided by 60 is 800 pi r teeth a second. And we worked. I hope you spent the 3 minutes working out how to have the number 10, because the answer is 4,000 teeth a second. All right. Uh, let's do this one. Pillars of the Amazon paradise have a radius of 1.2. At full throttle, they rotate at 135 revolutions per minute. What is the angular speed in radians per second? So how do you get revolutions per minute from revolutions per minute to radians per second? 135 revolutions per minute. And then how many radians are in a revolution? 2 pi. 2 pi radians per revolution. And then how many minutes are in a second? Or how many seconds are in a minute? 1 minute for every 60 seconds. Uh, Now you will see that this doesn't really cancel with this, but if you go left a little bit, you get minute and revolution and revolution. They're on opposite sides of the fraction. They can cancel with each other, and what you'll end up getting is 4.5 pi radians a second. That is the angular speed. The angular speed is in radians per second. It's how much you're turning every second, not the linear speed, which is v. Um, but we're going to calculate what the linear speed is right now in b. So what is the linear speed? The linear speed is, we worked it out, angular speed times the radius. So the linear speed is 4.5 pi times the radius, 1.2, which is 5.4 pi. What is the linear speed of a point halfway between the center of the propeller and the tip of the blade? Well, if it's halfway there, is it still going to be spinning the same? Is it still going to be spinning at the same speed? Is it still going to be spinning at the same angular speed? Is it still going to be spinning at the same linear speed? Well, let's think about it. Let's use this wheel to illustrate. So if you're right here, and this wheel spins 90 degrees, you get, yeah, you become, well, you go from here to here. If you're right here, this wheel spins 90 degrees, this will go from here to here. So the angular speed, no matter where you are, will stay the same. The angular speed will stay the same. Now that doesn't mean that the linear speed will stay the same though, because if you're closer to the center, the less you have to, the closer to the center you are, the less you have to move. If you take an extreme example, at the center, you're still spinning at a linear or at an angular speed, or maybe you wouldn't really be call it spinning anymore, but very near the center, you'd be still be spinning at that same angular speed, but you'd virtually not be moving at all. Um, so yes, the linear speed halfway will have to kind of simplify down to a smaller circle. In this case, it will be a circle that is this big rather than the entire circle. Why? Because now this becomes the circumference. This particular point now becomes the circumference, and we can calculate the length from this point, from the center to that particular point, halfway through the center and the edge of the blade, to get us 0.6. So the velocity is the angular speed times 0.6 meters, because the radius now 0.6 is only halfway between the center and the edge of the tip of the blade. So 4.5 pi times 0.6 is 2.7 pi meters per second. Do you want a third one, or did you ask that before I did my second example? All right, I'm still gonna be taking questions later. If you guys have more people who you would think that would benefit from asking questions, um, then please share it to them. Um, I'm mainly doing stuff from, well, I'm pretty much just gonna be exclusively doing stuff for honors pre-calculus or stuff dealing with algebra and functions. So if you ask a question that has, or if you share it to someone who's maybe learning algebra 2 or pre-calculus, that would be that would be great. But if you don't, yeah, but if you don't have any more questions, I will continue the presentation of the basic functions. We have this absolute value function. Basically just tells you the magnitude. So on the y or on the x plane, it tells you how far away you're from zero. So, well, if you're at this point, you're this far away from zero. So it's showing you, well, that's the number, or right there, this is the number that you are far away from zero. That this is the distance that you are far away from zero. If you're right here, that's the distance that you are far away from zero. You're a little bit farther. Even though it's negative, it doesn't say anything. It just says how far you are away from zero. That will be a lot more useful later on. Not really right now, though. Um, so the next basic function is x squared. Why is x squared basic? It's uh, it's one that you have to know. That's why. That's the main reason. X squared is a parabola. Ooh. Ooh. X squared is a parabola. X squared also has an even exponent. And x squared is also something we call even. X squared is even because it is symmetrical on the uh yeah, it is symmetrical about, so when you flip the right side of the graph to the left side, you will get the same graph. It's symmetrical about the y-axis. Y It has y-axis symmetry, so it's even. Absolute value of x also has y-axis symmetry, so it's even. Which actually provides you with a pretty good fact. The fact is that y equals absolute value of negative x is equal to the absolute value of x. But that's not very important. Let's keep going. Y equals x cubed. Y equals x cubed. Ooh. Ooh. That's what y equals x cubed looks like. This is flat right here. Right here, it's flat. Not very important to know, but I mean, it's more important in calculus, but it's flat right there, and it's always increasing. It's never really decreasing, or it's never decreasing at all. It's just always increasing. It's a strictly increasing function. And it looks like this, right? That's also the important thing. You also see this many times, so you better know it. Blank page. All right. Um, this next equation is y equals e to the x, which is the exponential, the natural exponential. It's natural because it's natural because of certain things that you do with interest, and if you're compounding continuously, what you will get is e to the x. If you're compounding interest continuously, eventually your multiplier will reach e to the x, and that's why e to the x is important, or the specific base e is important. So e to the x look like, I don't know if I've drawn it yet. I have not. All right, looks like this. The y-intercept, e to the 0, is 1. So this is 0, 1. Y-intercept is 1, and it has a horizontal asymptote, which I should denote with a dashed line. Let's do like yellow or something, or orange. Has a horizontal asymptote. What's an asymptote? The asymptote means that it approaches closer and closer to that line value, but it doesn't really ever get there. So this thing is approaching closer and closer to this value, but it never really gets there. Asymptotes. So lines can cross the line. You can have a line that's like this, and this would still be considered as an asymptote because this wave really this part of the graph doesn't really ever get there, but it's still an asymptote because well, it crosses it multiple times, but it will never get there. That's why it's an asymptote. But this one, EZX, that's more traditionally what we know as an asymptote, and that's how it works. Now know that vertical asymptotes do not exhibit the behavior where it can actually cross the line multiple times. Vertical asymptotes don't do that. If they do that, it's not a function. It's just straight and clear. It's not going to be a function. It's going to fail the vertical line test. It's going to fail a bunch of continuity understanding, and we're not going to get a function out of that. Now, the complete inverse of e to the x is, well, I guess there's two types of inverses, but one type of inverse of e to the x is the logarithmic inverse of e to the x. The logarithmic inverse of e to the x is natural log of x. Log base e to the x, which is natural log of x. Noted as ln. ln. I think in HPC I still wrote ln as ln. ln. But now I'm a little bit more educated. Now I can write cursive. So it looks like that. And inverses, a good fact to know about inverses, I'm just cramming a lot of stuff into your brain right now because I don't know when your exams are, but they're soon. They're as soon as tomorrow, so you better know the stuff. So a good fact about inverses is that they are actually symmetrical. They are completely symmetrical upon the line of the identity function. They're symmetrical on y equals x. So what you'll get for this is this. Something like this. And if I superimpose that same line, you will see that this can be reflected and give you this. Right? Pretty simple. This has a horizontal asymptote. So what does this have? This has a vertical asymptote. Right there. It approaches closer and closer, but never reaches there. All right. What is another basic function that we have? Another basic function that we have is the y equals sine x. So y equals sine x is a function that now how do you I don't know if you guys have trouble remembering what is the sine and what is the cosine. I remember the sine. I don't know why. I don't know what made it into my brain that made me realize this and attribute it to the sine. But the sine is the sine starts at the bottom, or the sine starts at the origin and waves. Right, the sine starts at the origin and waves. Cosine, which is another one of the basic functions, starts at the top, starts at the amplitude and waves. Why? I don't know. It just, oh well, I do know that the reason is if you put values of x, if you put values of x, y equals sine x is not sine theta. I'm sorry. But yeah, if you put values of x, sine x, cosine x, you'll get sine x will draw out the value of that, and cosine x will draw out this value. That's why. But I don't know what mnemonic to use. Just remember, sine x crosses the origin, cosine x does not cross the origin. How do you know? How could you know that? You could see that, well, sine 0 is 0. So sine 0 is 0. So x equals 0 means y equals 0. Crosses the origin. Cosine 0 is not 0. Cosine 0 is 1. So 0, 1 crosses, does not cross the origin. What else? We have more basic functions, but they're, well, these two you're gonna have to remember. But after that, they're gonna get a little bit convoluted. So this is y equals x to the minus 1. Or, the way that you probably see it more often, is that 1 over x. Alright, let me draw it a little bit better. That was pretty good. Alright, something like that. So this is y equals 1 over x. It is a hyperbola, which will be a word that you will see and you will kind of hate. This is not a parabola, it's a hyperbola. It's 1 over x. It looks like two curves, one in the positive x, positive y, one's in the or quadrant 1, and one in the negative x, negative y, so quadrant 3. Looks like that. 1 over x is important. It has a horizontal asymptote. It has a vertical asymptote. Horizontal, vertical asymptote. What else? If you shift it up, the horizontal asymptote will shift up. If you shift it down, the horizontal asymptote will shift down. It's the same with every single function. Every feature of the graph will also shift up and down with the graph. So it's not just going to be, yeah. And the limit, I don't know if you guys seen this notation. I'm just going to throw it out. The limit as x approaches infinity, which means that as you reach infinity, this is used to describe end behavior. So the limit as x approaches infinity of this graph, that means as we get to values of x approaching infinity, this f of x line right here approaches 0. So the limit as x approaches infinity of this graph, and the y value of that is 0. So, or you could just think of it numerically. If we put x equals 10, we get 0.1. X equals 100, 0.01. 1000, 0.001. Moves closer and closer and closer to 0. So as x approaches infinity, 1 over x is 0. Same thing for negative. Limit as x approaches infinity, or I'm sorry, negative infinity. So now we're approaching negative infinity. We're moving to negative infinity, not infinity anymore. So we'll have, well, if it's going, it's moving closer and closer to 0. So 1 over x is also 0. So that's the end behavior of this graph. And then the final one, out of the 12 basic functions, the final one that's really important, y equals square root of x. Now, I don't know if they're gonna make you learn the x to the 2/3 and x to the 1/3 as well. Those are pretty nice functions, but they're not very necessary. But they're pretty cool. Check them out if you want to. But y equals square root of x is important because the domain isn't the entire real number system, the entire real number spectrum, the domain is only from 0 to infinity. Why is this important? Well, first of all, 0 counts. Square root of 0 is 0. So, just because it's 0 doesn't mean that you can't put it in the square root. However, if it's 1 over x, if it's 1 over root x, 1 over square root of x, put 0 in there. That's not allowed. You can't do that. If it's 1 over square root x, the only section of the graph that will be visible is this section. So y equals square root of x is this right here. It grows slower than y equals x, but it grows faster than log x, or any type of log. So y equals square root x is going to kind of taper off. It is actually a translation, y equals x translation upon this purple line of y equals x squared. Where is it? Y equals x squared is a translation, but only the positive part of the translation, because y equals square root of x is only taking in positive numbers. So root x is the second inverse. Or no, I'm sorry, is the inverse of x squared, right? Root x is the inverse of x squared. All right, there are two more. I don't know if it'll test you on them. I really don't think so. The two more is y equals floor of x, or the greatest integer function, which basically all it does, all the graph is it rounds down every time. So if it's like, if you put x equals 0.5, it'll round down to 0. If you put x equals 0.8, round down to 0. So if you put x equals 3.5, rounds down to 3. So this is what the graph looks like. It's also called a step function. Kind of useless, but a great way to test whether or not you know your function transformations. And then finally, we have y equals 1 over 1 plus e to the minus x, also known as the basic logistic function. The basic logistic function goes like this. Has two horizontal asymptotes this time, not just one. The two horizontal asymptotes are the horizontal asymptote right here and the horizontal asymptote right here. And one's at 0. That's when e to the minus x is infinity. And one is at 1. That's when e to the minus x is 0, when x approaches infinity. And the turning point right here is 0.5. This is 0.5. And this is a basic function because it's actually a solution to a differential equation, which I just spitting crap right now. Right now, you won't know what those are until next year, but that's why it's important. Right now, it can also be used to actually model population growth. So the number, like if it's being used to model population growth, you can memorize a couple stuff like, well, if this is equal to a over b plus c e to the minus x, then the maximum population growth, or the maximum population that it will be, is when x approaches infinity, which means that it's a over b, because e to the negative infinity is 0. um or no, I'm sorry, is, yeah, e to the negative infinity is 0. So you get 0 times z, which is 0. So then you'll just get a plus b, or no, I'm sorry, a over b is the maximum population. Something like that. It's a better model of population than just exponential growth, because like us humans, we don't, animals don't really grow exponentially. They're limited by food and stuff like that. So this is a better approximation, this kind of S type curve. That's it. I will stop the stream once if you guys don't have any more questions in a couple minutes, I will stop the stream. I need to do some stuff. Um, but if you have more questions, then ask on. Yeah, no problem. All right. All right, I'm gonna end the stream now. I'm gonna leave the stream on. I think the other stream is on. I don't know. I'm not sure. Don't remember. But I'm gonna leave the stream on as well if is needed for reference. And I will see you guys next time.